Environmental disasters often begin with a single breach at the surface, a burst pipeline, a fractured oil rig, an aircraft that ruptures on impact, or an oil tanker accident. The 2010 Deepwater Horizon explosion killed 11 workers, and for 87 days, the oil leak remained unstoppable. The toll on the Gulf of Mexico was immense. Sea turtle hatchlings, dolphins, whales, fish populations, coastal communities, and human health all suffered severe long-term damage. Economic losses and mental health burden continues to echo across the region. Beneath the surface, the unseen damage was even more severe. More recently, in 2025, a UPS aircraft crashed near Louisville, Kentucky. That aircraft carried nearly 38,000 gallons of jet fuel, and it crashed near a facility that stored more than 226,000 gallons of used motor oil and nearly 37,000 gallons of oil-water antifreeze waste. Local authorities intercepted close to 30,000 gallons before it reached the waterways. Yet, response crews had to recover more than 286,000 gallons of oil-water mixtures from nearby ditches and streams. These accidents clearly show us how a modern-day industrial accident can turn into a severe environmental crisis. Our commonly used remediation methods have clearly not kept pace with the scale and frequency of these disasters. Burning the oil spill area causes significant air pollution. Chemical dispersants, which fragment the oil spill area into smaller oil droplets, but the use of dispersants are debatable as they are harmful to marine life. Skimming, which means collecting the spilled oil, is a slow and inefficient method and ends up collecting large volumes of water, which requires additional processing and energy. Collectively, these methods are expensive, difficult to deploy quickly, and only collect the oil that floats on the surface. They are unable to collect the oil that settles at the bottom of rivers and oceans, which is often the most damaging. But what if the very nature that we pollute every day is quietly holding the solutions to the problems we created? Nature has already engineered solutions that are highly efficient and sustainable. The lotus leaf is a powerful example. Water beads up and instantly rolls off from the surface of the lotus leaf. This natural phenomenon is known as superhydrophobicity, which is a surface that repels water. And this has inspired me to design sustainable surface technologies to tackle oil pollution. My goal is for each of you to see that the future of environmental protection lies not only in massive cleanup efforts, it lies in the small design of such nature-inspired surface technologies that can guide how water and contaminants interact, thereby stopping pollution by a surface at the surface. My PhD started in 2017 at the Indian Institute of Technology, Guwahati, India, in Professor Manna's lab, which specializes in nature-inspired surface materials. From 2017 to 2022, I worked alongside Professor Manna to develop sustainable surface materials to support oil-water remediation. In 2023, I joined UG as a postdoctoral researcher in the College of Engineering in Professor Hitesh Handa's lab, where I'm still trying to understand how chemistry and engineering can create new surfaces and open up new possibilities to protect our health, environment, and our future. But now let's go back to 2017, when I started my career in research with a surface. Not a complicated one, but just the surface of this cotton ball. Something that you all recognize. We use it to clean our makeup, clean our wounds, reach tight corners while cleaning and whatnot. It is soft, acts as an absorbent, yet quietly useful in so many parts of our everyday life. I did not have any grand visions for this cotton ball, but performing that one experiment, which turned this water-soaking, water-loving cotton ball into a water-repelling surface, just like the lotus leaf, completely hooked me. And I spent the next 5 years studying similar surfaces and designing sustainable surface technologies to combat oil pollution. During my PhD, I worked with leading petrochemical industries across India to design sustainable surface technologies for oil water remediation. Walking through those industrial sites and learning what real-world deployment demands showed me how big the gap still is between what we discover in the lab versus what actually reaches the field. Confronted with this disconnect between lab discovery and real-world deployment, I began digging deeper into the very well-studied yet remarkable surface of the lotus leaf. The surface of the lotus leaf isn't very smooth. It's covered in tiny bumps. They are so tiny that they are invisible to the naked eye and only can be observed under the microscope. These tiny bumps are actually made of wax that is secreted by the leaf itself. And we all know how water behaves around wax. Think of a candle. Water doesn't soak into wax. It sits on the surface of wax. The result of these tiny and waxy features on the surface of the lotus leaf is a thin, trapped air layer. Think of that air layer like an air cushion. So when a water droplet lands, it never really touches the leaf. It sits on that air cushion and instantly rolls off. And that's the secret for lotus leaves to stay clean and dry. So I am asked myself a very simple question. Can I give that same ability to something ordinary like the cotton ball? Using my background in chemistry, I made a liquid recipe containing water-repelling molecules to modify the surface of this cotton ball. And suddenly, cotton that normally soaks up water started repelling it. The key design takeaways for me were A, create tiny bumps on the surface, and B, make those bumps hydrophobic, just like the protective wax coating on the surface of the lotus leaf. So the next very obvious question was, can I use this super hydrophobic cotton for some useful application, like oil water remediation? If I use a piece of this water-soaking ordinary cotton ball to collect this sediment oil at the bottom, it is unable to do so because it instantly soaks up the water and it can no longer then soak the oil. However, if I use this super hydrophobic cotton, it collects this oil. Showing that it is selective only towards the oil phase. It does not leach out any toxic chemicals. It does not cause any secondary pollution. And most importantly, it is reusable. But how can we ensure that this technology and similar other innovations are implemented at an industrial scale and does not stay trapped inside a lab notebook? Real-world impact happens from testing materials in the messiness of the real world, scaling them beyond the lab, and designing them hand in hand with scientists, engineers, and industry partners, so that they can truly live outside the lab notebook. First, we need to test the product, not just in clean water, but in salty water, crude oil water mixtures, and emulsions, basically settings that are far more messier than what we use in academic experiments. Scalability. Can the product be made in kilograms and not milligrams? Can it be made using simple, safe, and affordable chemical approaches? can it be reused without losing its properties? If we want sustainable solutions, the product must be manufacturable. And finally, we need a collaborative spirit. Bridging the gap between academia and industry is not just about technology, it's about communication. True impact happens when scientists, engineers, and industry partners collaborate. Scientists need to think in terms of cost, logistics, durability, while industries must be open to new and bold ideas. I have worked with engineers in oil industries to test these products directly in their systems. This allows us to co-design materials that fit in existing setups rather than requiring entirely new infrastructure. The future of environmental protection will not be defined only by massive cleanup support efforts or billion-dollar infrastructure. It has the potential to be shaped by the quiet power of such surfaces engineered at the microscopic level to attract, repel, separate, and protect. As a scientist, I look to nature as a teacher and not just as a resource. I discovered sustainability on a tiny cotton fiber at the microscopic level. A single droplet, a single surface, and a single idea. As you leave this talk today, I hope you lean into the kind of science and curiosity that asks us to examine the surfaces and natural phenomena around us that quietly shape our world. Because the future of science does not only belong to laboratories and researchers like me, it belongs to all of us. Just as nature evolves through patience and persistence, science needs the freedom to think long-term, and that freedom depends on the choices made by students, educators, investors, consumers, and everyday citizens like you. And only then can we truly ensure that innovations like this cotton and countless other nature-inspired materials can move from scientific imagination to real-world impact. Thank you.